Next up, we have Sirina Nahban and Matthew Ramirez to tell us about JPL's Earth Science Mission, NISAR. Sirina graduated from the University of California, Riverside with a BS in Electrical Engineering in 2017. Today, she works as a systems engineer for the Deep Space Network, which enables missions that visit the moon and beyond to communicate with Earth. In her role, Sirina translates project data needs into software architecture in the DSN. Matthew Ramirez is a systems testbed engineer at the Jet Propulsion Laboratory, supporting the project NISAR as a part of the Flight Systems Engineering Integration and Test section. He is responsible for managing and conducting testbed operations. Matthew has been at JPL for almost 5 years and has previous experience in project formulation, verification validation, and fault protection systems engineering. Matthew is originally from New York City and holds a BS in mathematics from St. Joseph's College and is currently in his last semester of graduate school at Johns Hopkins University, expecting to receive a master's degree in space systems engineering.
Thanks everyone for having us here. So I first learned about Design Lab when I was an intern at JPL actually in 2016. And I went to the Design Lab opening and had a lot of fun. And now that I live and work in Pasadena, it's just really great to see Supply Frame's presence here, making Pasadena kind of techy. So I'll tell you a little bit about me and Matthew and a little bit about JPL, and then we'll get right into NISAR. Okay, so I'm an electrical engineer. I studied in the University of California, Riverside. Right now I'm pursuing a master's degree for space systems. And at JPL I do systems engineering for the Deep Space Network, which is a network of antennas around the world meant to communicate with anything that goes to the moon and beyond. I have a passion for outreach and space events. There's actually a really cool space event coming up called Yuri's Night. If you guys are interested, talk to me about it afterward. I got some NASA stickers here too. I'm really excited to be here. So everyone knows JPL because of these guys. So the rovers got a lot of attention in the media, but there's actually a lot that happens at JPL. Like for example, the Deep Space Network is completely managed through JPL along with their other foreign space agencies. There's all kinds of projects that employ all kinds of people from science to engineering, finance even. The kind of main pillars are Earth science, planetary science, and deep space missions. There's big missions and small missions that we call like garage shop missions that are usually built by in a low budget that can or can't become something. Like for example, the helicopter. I'm sure a lot of people saw that in the news. That started off as like a really small garage shop mission that sort of last minute got a ride on the rover and became this really great innovative thing. So like I said, NASA has 3 main pillars. Probably have heard of the recent asteroid missions, Voyagers, the deep space mission that's gone outside of our solar system. And just the main idea I want to give is, it's more than just space stuff. So when Magenta told me about the theme of the event, I thought it was really exciting because NISAR is currently being built at JPL right now, and me and Matthew took a walk down to the high bay where NISAR is, and you can see right here, NISAR is being built, and it eventually will kind of like stand out here, and they'll start working on it. So hopefully, when things open back up, we could do another tour one day. Okay, so a little bit about your speaker. Matthew majored in math. It was a math major at St. Joseph's from New York. He is about to complete his Space Systems Master's in Johns Hopkins University. He really has a passion for airplanes, so if you're interested in aviation or want to learn how to become a private pilot, he'd love to talk to you about that. He's been working on NISAR specifically for 3 years. He started off at Verification and Validation Department and moved on to fault protection, and now is a testbed engineer. And without further ado, I'll introduce Matthew.
All right. Thank you so much. That was a lovely introduction.
Sure.
Okay, so this is this project that I work at JPL. I've been working on it for around 3 years, starting my 3rd year. I've done multiple things within the same project, and so far I've learned so much about it, and I've entered like a more technical field of it, so I learned a lot about the hardware and the science goals, and I'm here to talk to you about it. So the project is it's called NISAR. It's an acronym that stands for NASA-ISRO Synthetic Aperture Radar. It's a joint partnership between NASA and ISRO. ISRO being the Indian Space Research Organization. It's essentially like India's NASA. And the objective of the mission is to study ecological systems of Earth, particularly its atmospheres, bodies of water, and the Earth's crusts. And it involves science, mostly involving climate change, or things that could lead up to climate change, or typical events that happen on, like in the Earth's crust, like volcanoes or earthquakes or things like that. And we want to measure those ecological systems using radar imaging so that we could either predict those events or see things about the Earth's environment and how climate change is affecting us. That's essentially the science we're trying to conduct. Its launch date, it was originally supposed to be this year actually, then it was moved to 2023, then we moved it again to 2024 because of COVID. But hopefully we can stay on track. Earth orbiting missions don't require a certain strict time schedule, like other missions do. For planetary missions, usually have a certain time period where they can launch a spacecraft because the Earth is closest in that trajectory. But this remains unaffected. The mission duration is 3 years. The budget is around $1.5 billion, which makes it a Class A. That essentially means it's the highest risk classification for NASA. Its orbit is sun synchronous. It basically means that it has an orbit in which you encounter like a 24-hour period where there's daylight and there's nighttime. And that kind of orbit is essential for NISAR because we can study the change within a certain part of the Earth and how it does over that time frame. Its altitude around 747 kilometers. That's around mid field elevation for an orbit. So there's low Earth orbit, mid, and then there's high Earth orbit. And then everything else is just inclination if you care about that. Then the launch vehicle is the geosynchronous launch vehicle. It's provided by India. Okay, so some of the Earth science. NISAR is a multidisciplinary radar mission, meaning that it can study all sorts of ecological systems. And the radar imaging allows us to study ecosystem disturbances like earthquakes, ice sheet collapse. You can measure the changes of bodies of water and how certain places in the Earth are changing over time, especially within like a year time frame. We'll be able to map using 3D imaging how that part of the Earth changes. And then you can also protect certain parts of the world by letting them know that there's potentially a hazardous event that's going to happen within the few, just with a couple months probably, studying the Earth's crusts and movements that go on that lead to earthquakes, tsunamis, volcanoes. And then it will optimize our study on these hazardous events by looking at the dynamics of the surface and interiors, studying the cold region, like the Arctic regions, bodies of water, and other ecosystems like forests. So NISAR is a partnership between NASA and ISRO. You can see in this picture, I think this was taken in 2014. This is the NASA administrator signing the agreement with the chairman of ISRO, where they decided on splitting the budget, essentially $1.5 billion, to have different contributions. JPL will contribute a certain amount of things, and ISRO would build the other half. So what we decided to do was JPL will build the L-band radar, the engineering payload, and the reflector mesh that we'll talk about and show you a diagram of what that looks like. And then ISRO will provide the launch vehicle, and they will build the S-band radar. And then also the spacecraft bus. So the spacecraft bus is essentially the thing that the payload will ride on. And it provides propulsion, telecommunications, attitude control, power, things like that. Okay. So these are a couple things about the spacecraft. This is one interesting fact is that it is the first spacecraft to use dual frequency radars. So this will have an S-band radar and an L-band radar. Essentially, we use two of them for different reasons. The L-band is a smaller frequency radar that allows us to look into primarily the surface of the Earth and the atmosphere. Because it has lower frequency, there's a bit more attenuation. And it won't be as good in looking in the interior of the crust. And it won't be good in bad weather environments or even a night sky. But it's really good for the surface and the atmosphere. So that's what we use the L-band for. And the S-band is higher frequency and there's lower attenuation. So you can look into the Earth's crust and get a more refined imaging or 3D imaging of all of the interior of the Earth's crust or polar ice caps, look inside volcanoes, and even measure the different substances that are produced by those environments, and get a full-scale picture, 3D image of it, so that S-band will work better for that. The payload consists of the two radars that are on a bus, and they have these actuators and boom that hold up a reflector. Yeah, this is good picture. Thank you. So the boom right here is like the stick that's holding up the mesh. The mesh is a reflector. It's made out of mostly steel that is the outer parts of the reflector. And then the actual circular part in the middle is it's like a soft mesh with gold platings on it. And what this will do is allow the radar to be emitted from the bus, and it will reflect onto the mesh and then create a ground swath that will shine onto Earth. And that swath is, I believe, around 150 miles. And it can measure something that's around I think it was around like 2 centimeters. It's really, really accurate. And of course, we're not trying to, measure a little rock, but to build a 3D image using radar, you can actually create a swath for a particular portion of the Earth and render the image to get a good screenshot of what the interior looks like for that portion of the Earth. See what types of compounds and substances can be found in that part, and then also take pictures over, let's say, 24-hour period and see how that part has changed. And that's essentially what the spacecraft will do for the course of 3 years. So you can get a lot of science on how the ecological systems change over time and get really high-quality imaging from using radars. It's called a synthetic aperture radar because the mesh actually increases the aperture of the radar itself by shining and reflecting from the mesh and onto Earth. And it's the first. There was a similar spacecraft called SMAP, the Soil Moisture or Passive Active Moisture Radar. It looks just like this actually, but the one difference was the mesh actually rotated. This one does not, but it was similar to that one. But that only had one radar. This is two, so it makes it a bit more interesting and get better quality. So this is the stowed configuration view of the spacecraft. As you can see right here on the right image, you have the NISAR electronic. That's the L-band radar attached to the spacecraft bus. The reflector is actually stored sort of like in a round cylindrical container, and then the boom is put away. So they connect. In this picture, they're disconnected, but they're actually connected in real life. But to just show the inside, the boom actually comes out very slowly, and I'll have a video to show you how that looks like. And they use actuators that, before using the actuators, they use pyrotechnics to detach it, and then the actuation brings out the mesh. And then once it's fully deployed, the mesh expands. And then we have the solar arrays on the sides. The spacecraft fairing is the thing that connects the rocket to the spacecraft. And then, so the bus is being built at ISRO. We're building this part over here, and including the boom. Everything is already built. We're mostly in the testing phase of the mission, but it'll probably take like another 2 years until it's fully integrated. So this will show the mesh deploying from the observatory. This is in the clean room. Yeah, this is how we test it. That's the fully deployed configuration. So I'm actually have the video paused for a second. Right there. Yep. So this is the high bay, is what we call. This is the clean room at JPL. The outer structure is made of steel, and the inside is like a very soft mesh with gold on it. And this video showed it pretty quickly, but this test took around 12 hours. For it to fully deploy, it took around 12 hours. And it'll actually take longer in space because you can't deploy it all at one time very quickly because it's a very high risk procedure. If this breaks, your mission is lost. It's very expensive, very complicated. The deployment part is probably the most tested procedure for the mission. And we have to simulate that using computers to try to get an idea of a simulated environment for space. And one of the biggest risk factors for this part of the mission is, and it's often overlooked, the space environment can be very cold and it can be very hot. And when it's deploying, it'll be in both temperatures. So because of the heat, the structure will actually sort of like get bigger. So the mesh will stretch because of the structure. It's made of steel and some aluminum. And when it gets cold, all of those structures will contract. So that expansion of the structure can lead to it breaking if you open it up too quickly. So you have to account for those changes in environments. And I believe it takes around a day for this whole sequence to complete. Next. Okay, so before I start this video, actually, the launch, from launch to deployed to like operation, I believe it takes around 2 weeks, technically around 12 days, but they still need to do a lot of tests before it actually operates. And this video will show you that whole sequence in a sort of fast motion. In this part, the spacecraft is already fully mounted and integrated into the launch vehicle. By the way, it's launching from India, so we actually have to ship the radar instrument to India. Yeah, so the geosynchronous launch vehicle has 4 rockets, 4 boosters, and it's able to launch anything up to high Earth orbit. So we can most certainly carry this. There was some sound, but I guess it wasn't. Yeah. So then here, the boosters have turned off. It separates from the launch vehicle and then unloads the fairing, leaving the spacecraft attached. When the fairing disconnects from the spacecraft, then NISAR will be on its own. It'll use its thrusters after the rocket has used them to keep it in orbit. Then it'll start its deployment sequence where the boom is detached. Then they move it over to 180 degrees. So that 90, then 180 degrees. And then it'll open up the second part. And it's fully deployed boom, but now the mesh has to unload. And then the wires have to expand until the mesh is completely rigid. Once it gets to this point, I think it's, what, day 11? Yep, day 11. So it takes about 12 days to up to calibration. And then it's ready for operation. So this spacecraft is, well, this mission rather, is very demanding. It's really hard to work with another country, especially since our systems engineering practices are very different. But it's been a very great mission to be a part of, and it will bring a lot of science that will give us a more accurate understanding of our climate situation, especially if you don't necessarily believe or understand how the Earth really does change over such a short amount of time, and it just exponentially increases over the course of 100 years. And the mission was started in around proposed in 2007 as part of the NASA Decadal Survey, where they essentially ask scientists or the science community, what kind of Earth science do you want to conduct? And once they figure out those parameters, people submit proposals to get that mission to be accomplished, explaining how you will do it, what kind of spacecraft you need, the instruments that you need, how much will it cost. And NASA took up this proposal and eventually proposed it and made it a flagship mission, meaning that JPL or NASA wanted to make it their own mission without contracting it out. But unfortunately, it's not an F-22 who wants to throw money at a science project. So it was really hard for them to get the funding. So then they needed a partner, and they asked India if they wanted to be a part of it, and they split the cost, they split the work, and that's how we got it to work. So yeah, it'll definitely be an instrument for bringing up more attention to our climate change, give us some more understanding for that scientific research in that field. So thank you very much. If you have any more questions, let me know.
Oh, and now we have a quick trivia question, really quick. Sorry, I know we're almost out of time.
Is there a prize for the?
There is a prize. It's a T-shirt or a hat,
Okay.
depending on your size. All right. Oh, okay.
Okay, let's do the question.
Okay.
Okay, so once the satellite is storing and collecting data, how does someone access or acquire or start using it?
Okay, good question. So actually, I forgot to mention that the spacecraft has what's called an SSR, a solid state recorder. It's basically the hard drive of the spacecraft. And when science data is when the radar signals are being emitted from the Earth back to the spacecraft, science data gets stored into the solid state recorder. Then it gets transmitted down via an antenna that uses Ka-band. Ka-band is a good frequency to use for high packaged data, and it gets transmitted down to a ground station. Then the ground station takes the data and has to unpackage it to make it readable, and then it gets sent to I think there's 2 universities, one in India and the United States, I believe Johns Hopkins and MIT and Stanford are part of it. They get all this science data, they evaluate it, they write it up into reports, and those reports are released annually as the science data gets reviewed and studied, and it gets published in many different research articles. And there's a database that actually you can access from the NASA website that gives you links to a lot of different sites that actually provide that data and it's public. You can get the raw data. It's really hard to understand that, but you can get the published data as well. And all of these universities study it and publish it. So and it's all peer reviewed, and you know, that's how we distribute it. Everything that's conducted by NASA is public.
Sorry,
Yeah.
no,
Oh, no problem.
Go ahead.
Oh, no problem. No, I want to get everyone's
Yeah.
Okay.
Oh, okay. Oh, and in the back, that was first. So are you saying that because? Yeah. So just to see if I understand the question, are you saying if that altitude would be a problem to the mission, or? Oh, yeah, of course. Okay, yes. I believe it is. A lot of the radar imaging is it's much more sophisticated than taking regular like imaging, and they have spectroscopy, but it's different because and let's start with imaging. With imaging, you can't get a 3D resolution of the things that you're trying to scan. And spectroscopy is more focused on how light is seen with the different types of materials within the Earth. With radar, you can map out the different topographies, you can map out the interior of the Earth without actually being able to see it from the surface. And with that capability, you do have an accurate measure of how deep those topography, I forget the word, but it's basically like the topographical structure of the Earth. So you get really high resolution of that. And the radars are actually very high powered. So for it to be able to reflect from the boom, reflect off the Earth, and return to the spacecraft, that's really good. And if you can observe that, you can map it pretty accurately. Okay, who should I get? But I will be here. See, I saw these two hands at the same time. Let's see. I'll come to you after. Yeah. Okay, so I'll start off by saying it's really difficult. And one reason, probably the major reason, is India's systems engineering practices are very different from NASA's systems engineering practices. And so India uses practices that were originated from the Soviet Union. They're very, honestly, they're very loose-ended. It's like you do everything individually. Everyone, it's very streamlined until you get to certain points. That's when you review things and integrate as you go. With JPL, there's a lot of red tape. I believe even in in North America at least, or at least like the Western countries, the systems engineering practices are very similar because they get the ideas from the NASA Engineering Handbook, for example. And all these companies, like especially like contractors like Northrop Grumman, Lockheed Martin, they use the same practices. And there's a lot of red tape, there's a lot of reviews, there's like critical design reviews, there's integration and test that goes along with different phases of the mission. You don't just test hardware and once it works, you just throw it in there and hope it works when it's all put together. It has a lot of different steps and a lot of strict rules. So when we're working with India, first of all, the time difference poses a really hard thing to work with, and then submitting everything, all the data and stuff. It's like, you have to contribute equally, but we also have to tell them what to do. And they get angry, and then they don't want to do that way. So it's really hard. And I could talk to more about it, but we're out of time. But, yeah.
Sorry.
No, it's okay. It's okay.
Music on, so go ahead, do your giveaway.
Okay, yeah. Okay, so the question is, which frequency, L-band or S-band, is a higher frequency with lower attenuation? Geo. The L-band, yes. Oh, no, actually.
Wait, no.
It's not the L-band, it's the S-band, yeah. Yeah. Yeah, I got it confused because the S-band is what Israel's making, the L-band is what we're making, and it's, yeah.
I got a backup one. How many active Earth orbiting satellites are going around right now? Active. Raise your hand and throw up a number.
Maybe we'll take the estimate.
Sarah? That's not a number, but I'm going to go with 1,000. Another? Anyone else? Joe? Yes? 6,000? You got... 6,001. Okay, all right. I'm gonna go with Xavier. I'm sorry, he was closer. It's about 7,000. Yep, active, and that's American and non-American. Okay, thank you. Come collect your prize afterwards. I also got some stickers here.